Hello, everyone. My name is Ruben Bridgewater. I'm a Node.js TSC member. I work as a principal software architect at Wolf, and I'm happy to be here today at the Node conference. And today I'm going to talk about demystifying memory leaks. So memory leaks are often considered something difficult and hard to solve. But is that actually so? And how can we ease that process? To get to that, I would first like to answer the question what a memory leak actually is. And I'm consulting Wikipedia to answer that question. So a memory leak is when a computer program incorrectly manages random access memory in a way that memory which is no longer needed is not released. As such, we are going to stack up more and more memory over time, and the program, in its worst case, might just crash because there is no more memory to allocate. And that's really the worst case scenario. Or maybe you're in a cloud environment and you're going to have to pay much more money because you have an autoscaling active and more memory is allocated there. So here we have a graph which clearly shows you how memory leak would look like in comparison to the memory usage and the time the program runs. And the yellow line is a perfect program pretty much. It starts up and you allocate some memory, and then there are some ups and downs, and this is perfect for each program pretty much. Sometimes spikes might be higher or going a little bit down again, but in average, it's a clear line, a flat line. And the blue line is a clear memory leak because over time, you allocate just more and more memory without actually freeing it again. And this is bad. So how do we handle memory in JavaScript in particular? Because we do not have to worry about it, right? This is all done transparently, and this is perfect. Memory is just freed. Why should there be a memory leak in the first place? So memory is divided into a stack memory and a heap memory. The heap memory is a dynamically allocated memory, and the stack is done by the operating system in a typical case. Each thread has some stack memory. It is a last in, first out algorithm, or also called LIFO. It's very simple, it's super fast, and the memory that is allocated on the stack is automatically reclaimed as soon as the function exits. When we compare that with the heap memory, there is a lot of things going on because the stack memory normally only contains pointers to the function that is currently running, and you push onto that stack the currently running pointer, pretty much. Then we get to the heap, which is the dynamically allocated memory. And here we have a nice overview from V8 that is done for the Times of India. There's a lot of things going on. JS objects are allocated. We have JavaScript source code, optimized code. We have regular expression code, strings, and much more. So this is the main memory for our program in this case. And the heap memory in V8 in particular is divided into three areas again. We have the young generation. So as soon as we allocate a new variable, let's say we say let foo is the string test, then you're going to allocate the memory test, and it's going to be put into the young generation. This memory is relatively small. Mostly JavaScript will have intermediate variables that you use to compute the next value immediately, and you do not need the variable as soon as you compute your next value. This is all done synchronously. So we want to dispose all of that memory that we do not need as soon as possible. So this young generation will only survive one so-called scavenge run. This is the first run where our program to free the memory is going to try to get rid of those not anymore used variables. And if any variable survives that run, it is then pushed into the intermediate generation. And if it survives the second run, then it's pushed into the old generation. This is the bigger part of the application. It's normally used for long used variables. So things that you reuse in each application that might hold pointers to a lot of things. And we use a different algorithm to free the memory in this case. And the algorithm used there is called mark sweep. We start off from a root object. The root object in a browser would be the window object, and in Node.js, it's global, while in modern JavaScript, it would be in both just global this. And we use it somewhat like similar to a recursive algorithm where we start off with the root object and we just connect each dot. We try to connect each node that is somewhat connected to that root object. All other nodes, all other variables or allocations are going to be freed. And this should be mostly ideal to free all the memory that is not used. So I already spoke about that we as a developer do not have to worry about the memory that we allocate because it's going to be automatically freed. What is done in the background is a so-called garbage collector is run. And that garbage collector has a lot to do. And at some point, it might actually even go haywire and does not work as we anticipated it would be. So we have to look into that a little bit closer. What are typical memory leaks or issues? This is in not a specific order, and not all are actual memory leaks. For example, the first two. So a wrong data type is still something that we have to look into because this is a very typical thing I frequently encountered. Often programs use memory types that are not efficient for the task that you want to solve. And then when you handle like with big data, you're going to allocate a huge amount of memory, even though you would not need that by just using a different data type. So using the correct data type can also help you to prevent your program to crash in case you once encounter bigger data. And the second one is we also try to run a lot of things in parallel. All of us probably love promises and async await. And we use promise all to improve the performance of the application because normally, like with Node, things are all run on a single thread. And we still want to do multiple things at a time, pretty much, to have multiple remote procedure calls. But when you just use too many of those at the same time, we also have to allocate memory for all of these steps. And when they are not yet done, they might also just cause an exception in your program because there is no more memory left. So this is also important to look into. Now let's go to the first actual memory leak, event listeners. So something a lot of people know is in browsers, like some while ago, it was typical to just attach event listeners immediately to a specific DOM element in a list that you would care about an event to be triggered from. And then we sometimes have to just add lots and lots of event listeners to all of these elements. Instead, you want to have a single event listener at a top node that would then listen to all the events coming from all these nodes below. And then you don't have to attach so many listeners because event listeners also add up in memory. And sometimes we just add a new event listener for each event incoming. This would be a program error, but it's frequently occurring. And more difficult is even the closures, because sometimes closures prevent the garbage collector from knowing when a variable is not used anymore and when we are able to dispose that memory. So this is a tricky one. Then file descriptors can also cause issues because when you open up a file, there's a limited amount of files you can open at the same time. And when we just run our program, it normally works even though we do not close the file after opening it. But this can cause issues as well. So we always have to make sure to close it on both success and non-success. So you should always have like a finally step, no matter if you were successfully opening that file or not, because sometimes there might be something in between and you still open it, but there was an error somewhere else and you still have to close that one. The most tricky part is that in JavaScript and when we look in Chrome or any Chromium-based browser, and Node.js is also run with V8, then we have to know some implementation details. I'm going to go into some of those in a bit. Here's an example for just how bad it can be if we read too much data in a single chunk as well. So we have an HTTP server, and we read a big file upon the user requesting a file. This is going to take a while, and it's not going to be efficient, and it's going to allocate a lot of memory because we first have to read all that memory into the application. And as soon as it's fully loaded, then we are going to start sending out that data to the user, not before. And when there is not a single user, but a lot of users requesting the same route at the same time, we might also have a memory problem because then just the total available memory is not going to be sufficient anymore, and the application is going to crash. Instead, we should just care about streaming the data in small chunks. It's going to be much faster, and we don't have to worry about the memory allocation anymore. We just get the first part of the file that we want to read, and no matter if it's like multiple gigabytes in size, we are still able to send it out immediately in, let's say, a few kilobytes. And as soon as it's done, it's going to be done. The memory line is going to be very flat. We don't have to allocate more than the small chunks that we want to read. And with the file descriptors, here we also cared about handling the error. We open up a file, we want to write something into it, but we never close that file again. And if we do that too many times, an application would also have a problem. So we should always make sure to close that file descriptor. And that's done in the final blog, as I spoke about before. The event listeners could look something like that. Let's imagine you have a database that is event-based, and you want to write something into it. And we have an event listener on data. So there's a HTTP server, and it wants to connect to a database, and it wants to write something into it. So we write into it, and then there's going to be a response, the data event. But in this case, we made a mistake because on each user request, we add a new event listener to that database instead of just a single one up front. And then we have a lot of event listeners in the end that are all very tiny, but it's going to end up as a blue line that you've seen early on. And this is the worst one, pretty much. It's a very frequently thing that is reported both on the Node.js issue reporting and on the V8 one, because this is an V8 specific part that you just have to know about. Strings are, let's imagine we have this very long string, 1 million characters long, and we just want to care about the very first 20 characters. So we slice out the 20, and normally you would imagine the rest is just freed because we don't use it anymore. Instead, we just have a reference because internally in V8, there's a lot of optimization going on, and it tries to be very fast and memory efficient at the same time. It's a heuristic that is used that might not always work as anticipated. Let's imagine we have the string test and the string ABC, and you want to concat it. Instead of allocating a new memory chunk that would consist of test ABC, it would just allocate a new very tiny thing, and that points to the test string and to the ABC string, and it would say, I'm the combination of both of these. So it's like a tree structure that you could imagine. And when we want to slice something out of it again, it's also just going to point to the original string and says, hey, I have this starting point and this endpoint of that string, but it's not going to free the rest of the string, even if it's not used anymore. And that could end up in a bad situation where we litter our program over and over. And as we all know, we should not litter our environment. It's still difficult to prevent, but we should care about it. Otherwise, the application might just crash, and this is the worst situation. And if it happens, well, we have to deal with that situation. And dealing with those memory leaks can be very troublesome. Sometimes we might even get some anger issues, and you spend a lot of time looking into something without really knowing what to look for. So we have to know how to identify the spots that cause that memory leak. And this is the most important part for me. So this is where we are going to focus upon now, how to detect and fix those memory leaks. There are a lot of tools and also flags to identify memory leaks in Node.js. The first one is a -- inspect that you can just pass to the Node.js runtime. And then you are able to connect, for example, to the Chrome inspector, but also to other tools. And we also have a flag that is called trace_gc. With the trace_gc command, it is possible to see what the garbage collector does at the current time. That's also interesting to know about. And sometimes it is very difficult to really still identify the bug. And then you might want to use the -- abort on uncaught exception, because this is automatically going to cause a so-called heap dump. And a heap dump is the state of the memory at that current point of time. So when the application crashes due to that exception, we can just then look at what the application was memory-wise at that state. And there are more tools like lnode to look into those. If you care about more tooling, just check out this website, nodejs.org, guides, debugging, getting started, and you will find a lot of information to do that. And I want to show you some coding, actually. For example, for the string one. So in this case, I have the small program, and I'm using the 8 module from Node.js. And we have a variable that is count. We just have it set to 0, and we have a variable foo. We have the function run, and this is going to do some things that we are going to look into in a second. We have this interval, it runs every millisecond. So the run function is triggered every millisecond. And then we create heap snapshots every 2 seconds. So we know what the state of the application is at that point of time. And here we have this inner function, and it is going to reference the original one, while original is again going to reference foo, and foo is updated on each run. So here we just confuse the garbage collector due to the way these variables are all connected with each other. And let's see what would happen in this case. Oops. This would be this one. So I want to check that program out. So now I am just open Chrome inspect, and due to the -- inspect flag, I'm able to now see the remote target. So I'm going to inspect this. And here you see this overview: select profiling type, heap snapshot, allocation sampling, etc. And I want to look into some of these heap snapshots. So I'm going to load one. And as you can see, the program creates new ones over time, each 2 seconds. So let's open up the first one, and let's open up the last one. And I'm also going to stop the program. Now we have these two, because here you can look into it, and there's like a lot of data going on, and it's not really sure what to look for. But we are able to compare it by just clicking on comparison. And now we can compare one of these heap snapshots with the other one. And then it's way easier to see where all your memory went into. For example, here we can see there's a big difference in the size delta of 2.4 megabytes. So this is clearly a point that we want to look into. And when we look into it, we see there's a lot of strings. These strings, again, when we look at them, say it's first in this variable, in this string, and the string is in a specific object at that memory point. And this is in original, in system context. Okay, context is in func. This is something we know about in our program. So we know func was here. This is our func. And then you can just identify the actual cause. We now know that it has something to do with func. Even though you don't see it immediately, we definitely know we allocated way too many of these strings, because you can see them all in here. They're very big and they are not freed. So you do know you have to look into that. My time is running short, so I have to hurry up a little bit, but I want to say this is also possible to use in a browser, because this tooling is just available there as well. And for example, you can start it. Click on it, okay. And by clicking on inspect, and then going to memory, and here is the overview of that as well. I want to show you a little bit more of another program right quick, for example, with the string crash. So here I have that problem that I've spoken about with the V8 one. We can look into the code. This is just doing exactly what I've spoken about earlier, and the program crashes very fast because it cannot allocate more memory. All right. So steps to fix the memory leak. First of all, please monitor your memory. Use, for example, an APM or something like that, and then you know how your memory profile looks like. Profile it with tools and like the inspect one, and take heap snapshots, but be aware they are very expensive. You do not want to do that in production in most cases. Always try to do it in a controlled environment that is there for testing. If you have to do it in a production setting, then you might do it with a very strict setting in a timeout, only a specific container or something like that, to only do it very infrequent. And then you can compare such heap snapshots. That's like one of the most efficient ways to identify the leak out of my perspective. And then you can just identify it and fix the problem as soon as you know what it is all about. There are lots of tools that may help you. You can check it out online on the website that I've spoken about. Memory is expensive, so not only cost-wise when you have to pay dollars or whatsoever currency for it, but also in the performance way, because when you allocate more and more memory, your system is going to slow down. So you really want to prevent that. Heap snapshots are expensive for a similar reason. It is going to be like a frozen application at that point of time. It can't do anything else while gathering up all the memory of your application. Carefully choose your data type and your data structure, and only restart your application as a last resort. Try to fix the actual issue instead. So thank you very much for being here. I want to end with one of my favorite quotes from Ken Thompson. One of my most productive days was throwing away 1,000 lines of code, and I can very well relate to that. Have a great day.